We'll get started in a few minutes. All right, I think we can get started now. So, a quick introduction. Today we'll be going over the MOAA, which is the Math Open at Andover. It's a math competition for middle schoolers. And today we're going to be over some problems from the one that just happened last month. So again, some information. It's held each year in October. You can either take it online or you can take it in person at Phillips at Andover Academy in Massachusetts. the team-based contest, and each team can have up to 4 people. Individuals and teams who score high will receive prizes. This year, the prizes included t-shirts, books, toys, and trophies. So now I'll be explaining a bit about the format of the contest. It's organized in 4 rounds: the speed round, accuracy round, team round, and Gunga Bowl. The speed round and accuracy round are individual rounds, and the team round and Gunga Bowl are team rounds. So individual rounds are worked individually by yourself, and the team rounds are done together as a team. Speed round has 15 questions to be solved in 40 minutes. The accuracy round has 10 questions to be solved in 50 minutes. The team round has 15 questions to be solved in 40 minutes. And the Gunga Bowl has 9 rounds, each with 3 questions to be solved in 75 minutes total. There will be a live scoreboard for the Gunga Bowl. The questions range from low AMC 10 level to high AME level. And in each round, the difficulty can vary, but generally the speed round is easier than the accuracy round. And in each round, the question difficulty increases as the problem numbers increase. And I'll post a link in chat for more information about the Gunga Bowl. About the MOAA. Okay, I think now we can get started on the problems. So this is problem 3 of the speed round this year. I'll give you 5 minutes to think about it. Okay, I think we can start going over this problem now. So first, what we want to do is we want to split up 6 to the 10 into 2 to the 10 times 3 to the 10. So basically, this is the prime factorization of this number of 6 to the 10. And now we can write out its factors. We notice that if some number is a factor of this 6 to the 10, then it has to be a factor of this 2 to the 10 times 3 to the 10. And that means it has to be of the form 2 to the a times 3 to the b, where a and b are positive integers. And both of them are less than or equal to 10. And so if this number is odd, if this factor is odd, that means it has no factors of 2. That means that a has to be 0. And now, if we think about actually choosing a random prime factor, a random positive factor, then what this will mean is that the choices for a and b are independent. So whatever you choose for a doesn't affect what you choose for b, and whatever you randomly choose for b doesn't affect what you choose for a. And choosing a random factor just means choosing 2 random values of a and b that satisfy these conditions. So then notice that a can be 0, 1, 2, so on to 10. And selecting a random value of a means picking a random number from these 11 numbers. And it's only odd if a is 0. So the chance of it being this one out of these 11 choices is 1 over 11. So m equals 1, n equals 11, m plus n equals 12, which is the answer. Are there any questions? Okay, if not, then I think we can move on. So this problem was from the team round. It was problem 5. And again, I'll give you 5 minutes to think about this. Okay, I think we can start going over it now. So the way to solve this problem is by casework on the number of digits. So if it's a positive integer, then, well, it obviously has to have at least one digit. So first we consider if it has just one digit. So if it has just one digit, then we can call the number A, and that's also the digit. So then the product of its digits, well, it's just A, and the sum of its digits is also just A. And then this is the sum of the product of its digits. So we can simplify this. A equals 2A. So basically A equals 0, but that's not a positive integer, so it doesn't work. Next, we look at if it has two digits. Consider the number A, B, where A and B are digits and are not multiplied. Now, we know that if we can write a number, if a number can be written as A, B in digits, it can also be written as 10A plus B. So then this equals the sum of its product of its digits, which is A, B, and the sum of its digits, which is A plus B. We can simplify this equation to get 9A equals AB. And in a positive integer, the leading digit can't be 0. So A can't be 0, so we can divide by A. And we get B equals 9. So this tells us that it doesn't matter what A is as long as B equals 9. So we can set A to be anything. And we want this to be the smallest positive integer. So we let A equals 1, B equals 9. And the answer is 19. And we can check that this works. We get 19 is equal to 9 plus 10, since 9 is 1 times 9 and 10 is 1 plus 9. So then 19 is our answer. Are there any questions? Okay, if there's still no questions, I think we can move on. So this problem was problem 11 on the Gunga Bowl. I'll give you 5 minutes to think about it again. And just as a reminder, please send me your answers in chat if you have solved it. And please do it as a direct message so that not everyone can see the answer. Okay, I think we can start going over this problem now. So first thing we notice, if this number is a multiple of 99, since 99 equals 9 times 11, it needs to be also a multiple of 9 times 11. So it needs to be a multiple of both 9 and 11. And now we can use our divisibility rules. First, divisibility rule of 9 tells us that 1 plus a plus 2 plus b plus 3 plus c plus 5 plus d plus 6 plus e has to be a multiple of 9. So the way you can write that is it is equivalent to 0 mod 9. And we can simplify this to 17. So first, let's let a plus b plus c plus d plus e, let's let that equal s. So then when we simplify this, we get 17 plus s is 0 mod 9. And 17 is congruent to -1 mod 9. So we can also write -1 plus s is congruent to 0 mod 9, or s is congruent to 1 mod 9. And now let's look at what the divisibility rule for 11 tells us. We get 1 minus a plus 2 minus b plus 3 minus c plus 5 minus d plus 6 minus e is a multiple of 11, or is 0 mod 11. And we can simplify this again to 17 minus s is 0 mod 11. And we can reduce 17 to 6 mod 11, so 6 minus s is congruent to 0 mod 11. So solving this, we get s is congruent to 6 mod 11. So now we can solve these two equations. And we have one other fact. We know that all of these a plus b plus c plus d plus e, each one of those digits is less than or equal to 9. So then we also have s is less than or equal to 5 times 9, which is 45. So we want to find a number s such that it's 1 mod 9, 6 mod 11, and less than or equal to 45. And it also has to be positive since, well, all these digits are positive. So then their sum has to be positive as well. Actually, sorry, it has to be non-negative since each of these digits can be 0. So we also have s is greater than or equal to 0. So now we can check these numbers. And we can check the numbers that are 6 mod 11 and see if they're also 1 mod 9. And we can list them out. 6, 11, 17, 28, 39. And the next one, 50, is already greater than 45. So that doesn't work. So now let's just look at these four. We get 6 is 6 mod 9, 17 is 8 mod 9, 28 is 1 mod 9, 39 is 3 mod 9. So since 28 is also 1 mod 9, we get that the answer is 28. Are there any questions? Okay, if there's no questions, we can go on to the next problem. This problem was problem 12 on the Gunga Bowl. And again, I'll give you 5 minutes to think about it. Okay, I think we can start going over this problem now. So the first thing we have to do is to draw a diagram. So hold on. So okay, we have AB equals 10 and all the other sides are 6. So then triangle ABC has sides 6, 6, and 10. And what we notice is that point D is the same distance from each of these. It's all 6. And then this is a 3D problem. So if you think of it as a plane of triangle ABC along with point D, if you drop the altitude from D down to this plane ABC, you get another point. Let's put it that point here. Let's call it M. And then what we notice is that since M is the foot of the altitude from point D down to the plane of triangle ABC, we get angle AMD, angle BMD, and angle CMD are all right triangles. So then we have that AD squared minus DM squared equals AM squared. BD squared minus DM squared equals BM squared. And CD squared minus DM squared equals CM squared. And what we notice that since AD, BD, and CD, AD, BD, and CD are all the same, and then DM is always the same, we get AM equals BM equals CM. And since M is on the plane of triangle ABC, we get M is the circumcenter of triangle ABC. So now we want to find the volume of this tetrahedron. And we do it by trying to find the base and height. And we can calculate the base as the area of triangle ABC. And the height is just dm. And what we're looking for is the volume of this, which is 1/3 times the area of ABC times dm. So let's find the area of ABC. Well, using Heron's formula, we can pretty easily get that the semiperimeter of triangle ABC is 11. So the area is square root of 11 times 5 times 5 times 1, which is 5√11. And then, so that's the area of ABC. And then to find DM, we know AD, and we know that AMD is a right triangle. So if we can get AM, then we'll know DM. And AM is easy to find since it's the circumradius of triangle ABC. And for any triangle ABC, the area is the product of those 3 sides divided by 4 times the area. And well, we already know what the area is, and we can get ABC easily. And we get it 6 times 6 times 10 divided by 4 times 5√11, which simplifies to 18 over √11. And right now I'm not going to simplify this just so it's easier. And now we have AD equals 6. AM equals 18 over root 11. And we have DM equals the square root of AD squared minus AM squared. And we can calculate that. We get this is square root of 72 over 11 if we do it, or which is 6 root 2 over root 11. So we can plug these into our formula. And the root 11s cancel. And the 1/3 times the 6 equals to 2. And what we're left with is the volume is 10 root 2. And it asks us for the square of the volume. So this squared is just 200, which is the answer. Any questions? Okay, if there's no questions, I think we can move on. This is problem 15 on the Gunga Bowl, and I'll give you 5 minutes to think about it. Okay, I think we can start going over this now. So we can do this by actually working backwards. So instead of being looking at 1, first let's draw a number line. 1, 2, 3, 4, 5, 6. Instead of first putting it at 1, let's put him at 5 instead. And let's see the chance that he reaches 6. Let's suppose he's at 5. Well then, if he's at 5. He has a 1/3 chance of moving 1 unit to the right and landing at 6. In which case, there's probably 1 chance that he reaches 6, because that's obvious. And then if he moves either 2 or 3 units to the right, to the 2/3 chance of happening, then he'll skip over 6, and he'll never be able to go back to it, since, well, you can only move to the right and you can't move back to the left. So then in this case, the probability is 0 that he'll reach 6. So then if you're at 5, the probability that he'll reach 6 at some point is 1/3. Now suppose you're at 4. Now there's a 1/3 chance that he goes to 5. And then once he's at 5, well, we know that the chance that if he's at 5, then he'll reach 6. That chance is 1/3. So then there's a 1/3 chance he makes it to 5. And then a 1/3 chance that from there he reaches 6. And then it's also a 1/3 chance he moves 2 units to the right and just lands on 6. Which is also probability 1. And then finally there's a 1/3 chance he moves 3 units to the right and skips 6 entirely. That's probability of 0. In total for 4, we have there's a 4/9 chance that he'll reach 6 if he starts at 4. Now let's look at if he starts at 3. There's a 1/3 chance he moves 1 unit to the right, lands on 4. And from there, there's a 4/9 chance that he reaches 6, as we already found. There's a 1/3 chance that he moves 2 units to the right, lands on 5, and from there, there's another 1/3 chance. And then there's a 1/3 chance that he jumps 3 units to the right and lands on 6, and that probability is 1. And we get that this equals 16/27. So if he's at 3, he has 16/27 chance of reaching 6 eventually. Now moving back to 2. The 1/3 chance that he moves 1 unit to the right, in which case he lands on 3. From there, there's a 16/27 chance. So 1/3 chance that he moves 2 units to the right, lands on 4. From there, we get a 4/9 chance. And from there, there's a 1/3 chance he lands on 5. There's another 1/3 chance. We get that this equals 37/81. And now finally, moving to 1. And for 1, we have 1/3 chance he moves 1 unit to the right, lands on 2. And there's a 37/81 chance that he'll eventually reach 6 from there. Then there's a 1/3 chance he lands on 3. And there's a 16/27 chance he reaches 6. And there's a 1/3 chance he lands on 4. Then there's a 4/9 chance you have on 6. And then if we calculate this, we get that this is 121 over 248. Sorry, over 243. And these two are relatively prime. So get the answer is 121 plus 243 equals 364. Are there any questions? Okay, if not, I guess we can move on to the next question. This problem was accuracy around problem 7, and I'll give you a few minutes to think about it. Okay, we'll go over this now. So this problem is kind of similar to the last problem. And let us define a function f of n, which is this expected number of draws for some n number of balls. So for example, what we're looking for is f of 16. And based on this, we can find an equation for f of n. So there's n balls total, and she draws three of them. So the chance that she draws the blue ball immediately is 3 over n, in which case the number of draws is just 1. And the rest of the time, the n minus 3 over n chance is she draws 3 red marbles. So then she discards one of them. And now it's the same problem again, but with f of n minus 1. And well, we've already used up one move on one draw on that. So we need to add another +1 to that for the expected number of draws. We can simplify this to f of n equals 1 plus n minus 3 over n times f of n minus 1. And now we can start computing small values of this function. So we see that f of 3 equals 1. F of 4 equals 1 plus 1/4. F of 3, which is 5/4. F of 5 equals 1 plus 2/5 times 5/4, which is 6/4, and I'm going to leave it unsimplified for now. F of 6 equals 1 plus 3/6 times 6/4, which is 7/4. And hopefully you can see a pattern. It seems that f of n is just n plus 1 over 4. And we can actually show this by induction. So we obviously see that for f of 3, this is true. This is the base case. F of 3 is equal to 3 plus 1 over 4. And now suppose it works for some f of n. This equals n plus 1 over 4. We want to see some f of, we want to show this is the same for f of n plus 1. And from our formula, we get this equals 1 plus n minus 2 over n plus 1 times f of n. But then we know what f of n is. So we can replace that by n plus 1 over 4. And these two cancel. So we are left with f of n equals 1 plus n minus 2 over 4. Simplifies to n plus 2 over 4, or n plus 1 plus 1 over 4. So our induction is done and this is proved. Now we can plug in f of 16, which equals 17 over 4. These are relatively prime, so 17 plus 4 equals 21. And this is our answer. And are there any questions? Okay, if there's no questions, then we can move on to the next problem. And I'll give you 5 minutes to think about this. Okay, I'll start going over this now. So we can start by graphing this function. So first, let's graph the function y equals x to the fourth. Look something like that. Now let's graph y equals x to the fourth minus 1. And basically what that does is it just moves it down. It just moves the whole graph down by 1. And now let's graph y equals absolute value of x to the fourth minus 1. So if you're wondering what the absolute value means when graphing, just means take all the parts that are negative, that are below the x-axis, and reflect them over. So this is the graph of y equals absolute value of x fourth minus 1. And now the problem asks for a line that intersects this at 4 points. Points A, B, C, and D. And it tells us that BC equals 2AB equals 2CD. Well, we can see that this graph is symmetric in so that if you swap the x, if you replace x with negative x, this expression will stay the same, since x to the fourth equals negative x to the fourth. So then this expression stay the same. So then it's symmetric over so then the graph is symmetric over the y-axis. You can reflect it and it still stay the same. So now let's suppose this line intersects the y-axis at some other point M. We know that BC equals BM plus MC equals 2MC from the symmetry, and we get M from this that equals 2CD, or MC equals CD. Now suppose this line is y equals k. Y equals k intersects the graph at 4 points, and when x is positive, it intersects at the points C, D. So now let's suppose k equals absolute value x fourth minus 1. Let's find the solutions of this. Well, we see that this is either x to the fourth minus 1 equals negative k, or x to the fourth minus 1 equals positive k. And in this graph, we see that the part closer to the y-axis has been reflected across the x-axis. So that means that is the part that the absolute value has modified. Notice that this part is changed, but this part is not. So that means that this is where C comes from. This is where the D comes from. Since if you just remove the absolute values, that equation would look like the equation for D. And if you remove the absolute values in the graph, then D would still be the same point, but C would not. So let's look at the solution for each of these. For C, we get that x to the fourth equals 1 minus k. And we know that C is positive, so x is the fourth root of 1 minus k. Similarly, we get x fourth equals 1 plus k for D. So in this case, x equals fourth root of 1 plus k. Now we have that these two are the x coordinates of points C and D, and we have that MC equals CD, and the x coordinate of point M is 0. So that means the x coordinate of point D is 2 times the x coordinate of point C. In other words, 2 times this equals this. So now we solve this equation. We take this to the 4th power. You get 16 times 1 minus k equals 1 plus k. 16 minus 16k equals 1 plus k. 15 equals 17k. K equals 15 over 17. And these are relatively prime. So we get 15 plus 17 equals 32, which is the answer. Any questions? Okay, if there's no questions, I guess we can move on to the next problem. This was problem 17 on the Gunga Bowl, and I'll give you 5 minutes to think about this. Okay, we can go over this now, I think. And now for this problem, the first thing we notice is that each move changes the value x plus y. Each walk changes the value x plus y. This increases by 2, no matter what walk he chooses. For example, if you choose the first block, then x plus y becomes x plus 2 plus y, or x plus y plus 2, and it's still increasing by 2. Initially, we have x plus y equals 0, and then at the end, we have x plus y equals 20. Each move adds 2, so that means there's a total of 10 walks. So we have 10 walks. Now we look at x minus y, how this changes. Initially, it starts at 0 and ends at 0. And the first walk and the third walk both change this. Both the first block increases it by 2. First block makes this x minus y plus 2. And the third block decreases by 2. It makes it x minus y minus 2. And the second block leaves it unchanged. Since it goes from 0 to 0, we have the same number of first blocks and third blocks. And now it can be helpful to label these walks by numbers 1, 2, 3. So basically, you can represent his sequence of walks by a 10-digit string of numbers. Each number is 1, 2, or 3, such that the number of 1s and 3s are the same. And, well, there's no 2s in a row. So then, since the number of 1s and 3s are the same, the number of 1s and 3s in total has to be even. 10 is even, so then their difference, which is the number of 2s, is also even. And we can do casework on the number of 2s to solve this. So obviously, we notice that if there's 10 2s, then no matter how we arrange them, there's only one way to arrange them. He'll have 2 brilliant walks in a row, which is impossible. And similarly for 8 and 6 walks, 6 to 2s, that'll be the same case. There'll be 2 2s in a row. So then we start with 4. So then we start with the case that there's 4 2s. Let's put the 2s in an arrangement like this. Just an example. And we want to find how many arrangements of 2s can we do. And what we get is that, so the way to do this is actually, we notice that we count the gaps. This is a gap. This is a gap. This is a gap. This is a gap. And technically there's another gap right at the end. And then this condition means that, well, this gap can be at least of size 0. This gap has to be of size 1. Has to be greater than or equal to size 1, since no 2 2s can be in a row, and that would make it at a gap size 0. This has to be also greater than or equal to 1. And also this, and then this is just greater than or equal to 0. And then we notice that since there's 4 of these and 10 in total, there's 6 possible gaps. There's 6 possible spaces that we can split into these 5 gaps. And then if we subtract 1 from each of these, we get 0. We change these all to 0. The number of gaps goes down to 3. And we're looking for the number of ways to split up, to partition 3 into 5 numbers. For example, 1 1 0 1 0 1, so that they add up to 3. And we can do this by stars and bars. And basically what that is this can be represented by a sequence of 4 bars and 3 stars. So then this gives the sequence star bar star bar 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 star, which corresponds to this 11001. And basically for any sequence we can have, you can generate this, the 4 bars, separate this into 5 gaps, and those 5 gaps have the 3 stars together. And the number of ways we can arrange this is, well, there's 7 shapes in total. And then we can choose which 3 of these are going to be stars. That's 35 ways. So then once you choose the 3 of these to be stars, the rest of them have to be bars. And each of these corresponds to one of these. Each of those corresponds to one of these. So that means there's 35 ways to arrange the 2s. And then for the 1s and 3s, there's 6 spaces left. We can choose 3 of them to be 1s, and then the other 3 are going to be 3s. We can do that in 20 ways. So in this case, there's 35 times 20 equals 700 total ways, in the case that there's 4 2s. Now on to the next case. If there's only 2 2s, this gets easier since we can do complementary counting quite easily. We notice that there's only 9 possible ways to arrange the 2 2s. I'll put them next to each other. And in total, we have 10 choose 2, which is 45. Total ways to put the 2 2s. And then 9 of these don't work. So we have 36 ways that do work. And then we can arrange the 4. Then there's 8 left over. And then these must be 4 of them have to be 1s, 4 of them have to be 3s. We can choose the position of the ones in 8 choose 4, which is 8 times 7 times 6 times 5 over 24, which is 70 ways. So that 36 times 70 equals 2,520 in this case. Now the last case, there's 0 2s. Then we can choose 5 of these to be 1s, and the rest of them have to be 3s. 10 choose 5 ways. 10 choose 5 equals 252. So that's another 252 ways. Then adding these together, we get 3,472 total ways, which is the answer. Are there any questions? So I guess there's no questions. Well then, I guess we're running out of time, so I guess this is the end. If there's any last questions, please ask them now, and I'll be ending the meeting soon.